Great. Hello from the Adler Planetarium. My name is Andrew Dawson. I'm the Vice President of Astronomy and Collections at the Adler Planetarium. We're really happy to be with you today. As you know, we're celebrating 50 years since the mission of Apollo 13, one of the most well-known stories in the history of space exploration. What we're doing is we're getting some insight from people that were actually part of the mission 50 years ago to get some of the details and share some of the lesser-known stories about that mission. Today with us is Norm Chaffe. He's speaking to us from Houston. Hello, Norm.
Hello, Andrew. Nice to talk to you.
Nice to talk to you. Norm is retired from NASA. He was a chemical engineer. He worked on a lot of the thruster systems that made it possible for the spacecraft to get to the moon and back. People often don't know that the Apollo spacecraft actually had sort of 2 or 3 spacecraft in one, and they had multiple systems to get there. And he worked to make sure that all those thruster systems worked appropriately. And he was also on the ground during Apollo 13. Before we get to Apollo 13, Norm, I wanted to ask a little bit about your time at NASA. Tell us really briefly, what did you do before you worked at NASA? How did you end up being a chemical engineer there, working on getting people to the moon?
Well, as a kid, I had always wanted to be a chemical engineer. I was raised in Tulsa, Oklahoma, which at that time was called the oil capital of the world. My family knew a lot of engineers. They were petroleum engineers or refinery engineers, and most of their degrees were in chemical engineering. I loved chemistry, so it was just a natural for me to want to do that. When I graduated from high school, I was given a full ride scholarship at Rice Institute, which is here in Houston, now called Rice University. And so that made the decision for me about where I was going to come. I came to Rice. I stayed here for 3 years studying chemical engineering, fully intending to go into the petrochemical or refinery business after I graduated. And a situation required me to be back in Tulsa. So I transferred to the Tulsa University, where I got a bachelor's and a master's degree in chemical engineering. And I got the best of both educations, because the Rice professors taught me all the equations and the Tulsa University professors taught me all the practical tricks of the trade. So
right.
when I came to NASA, I was one of the few chemical engineers with a petrochemical refinery background, but I was very comfortable with dealing with the propellants and the unusual chemicals that they were dealing with that befuddled the mechanical engineers and the electrical engineers.
Yeah, I can see how that's an important insight to bring to the table, right? Your the chemistry of how these propellants work and their thermal properties and so forth. It's always interesting to hear people with different backgrounds bring something unique to make these missions work. So I mentioned earlier that there's. Let's talk a little bit about the propulsion systems on Apollo. It really was a complex challenge, right? I mean, there were actually 3 whole separate sets of thrusters that had to work, and you worked on how to make sure those thrusters would work and continue to work. The mission going all the way to the moon and back. Talk a little bit about that. First of all, give us a little bit of background. What were those different systems, and how do they all work together to get this spacecraft to the moon and back?
Well, first of all, there were actually 3 separate modules that constituted the Apollo spacecraft. The command module was a capsule, looked like a little cone, had the heat shield on the back of it, and that's where the 3 astronauts nominally rode to and from the moon. Behind the command module and attached to it for all of the mission except the final Earth re-entry was something called the service module, which contained their large 20,000-pound maneuvering engine if they needed to change their trajectory going to or coming from the moon, and also included the little steering rockets called reaction control system rocket engines. And the 3rd module was the Lunar Module, which was a separate spacecraft completely, It would separate when they got to the moon and into lunar orbit. It separated from the command module. It went to the moon, docked to the command module in a nose-to-nose position, so the crew could transfer back and forth. When they got ready to descend, the two astronauts that were going to descend transferred through a tunnel into the lunar module, separated, and went on their way. And so they had a separate, completely separate spacecraft from the command and service module, which stayed in orbit. And actually, in the Mission Control Center, we had two active control rooms when the lunar module was active.
One for each.
One for the lunar module, one for the command and service module. So that was the intended scenario. Once the lunar module was through with its mission on the surface, returned and docked with the command and service module, and the crew transferred back, it separated and crashed itself on the moon. And the command and service module then left lunar orbit and spent a couple of days coming back to Earth. The service module was jettisoned just about the time they entered Earth's atmosphere, and only the command module entered with the crew.
And we have those command modules in museums here on the Earth today. The lunar modules all stayed on the moon. Well, the ones that made it there, anyway.
That's right.
Now, when we talk about these thrusters, sometimes we like to give people an idea of what these things look like. And you have a pretty good show and tell item to share with people right now.
I do. Each of the modules had their own system of small 100-pound thrust rocket engines. And my assignment when I reported to NASA was to become an expert in and work on those. So I helped with the design, development, test, and what's called certification of those pieces of hardware, as well as the rest of the system. So I brought one with me. And can you see that, Andrew? Does that show up well?
I can see you right now. Your image quality is a little bit low. We'll if you hold it still, yeah, hold it up just a little bit. There you go. So what he's holding right there is one of these thrusters. Now, this would have been from which vehicle?
This is a 100-pound thruster, and there were 16 of these on the service module and 16 on the lunar module.
Yeah, so people have seen pictures of the spacecraft. You can see that now the image quality is really good. These are the little rocket nozzles on the side. They're sticking out the side of that cylinder-shaped service module, and this is one of those that he's holding right there. And go ahead. Yeah, go ahead.
This thing in the middle is called the Combustion Chamber. It's made out of an unusual metal called molybdenum, which is on the chemical chart of chemicals.
Yes.
That's right. This valve up here is a fuel valve, and the valve over here is an oxidizer valve, and this area back here is the expansion nozzle. This little area is called the throat. So the fuel was exotic material called monomethylhydrazine. The oxidizer was a material much like ammonia called nitrogen tetroxide. And when you squirt them together, you didn't need a spark plug to light them. The two chemicals were so reactive with one another that as soon as you squirted them in there through 8 little orifices and they splashed together, boom, boy, they were off and running. And the interesting thing about these little engines, as compared to the launch engines that most people are familiar with, is these typically only fired for very, very short periods of time. And so they were called pulses. Right. You could open the valves and fire them until all the fuel an oxidizer was gone, for 20 minutes. And when you did that, if you fired steadily for over 30 seconds, this molybdenum combustion chamber, which is gray here at room temperature, would get up to about 2,900 or 3,000 degrees, and it would be incandescent, just like a light bulb is. And so it was very interesting to watch a long firing and watch this thing go from gray to red to orange to white,
Which would, of course, hopefully never happen during a mission, an extended.
Well, unless we needed them, and occasionally we did use it. So they were capable of doing that. But the most of the firings that this little engine did were at 14 milliseconds
Oh, wow.
length up to maybe 100 milliseconds.
But
So
one of the things about the people sometimes surprised to hear, you can put the thruster down now.
Okay.
It doesn't. When you said it's a 100-pound thruster, just people understand it doesn't mean it weighs 100 pounds. Norm isn't that
it gives 100
right.
100-pound force.
But the lines that feed into this sometimes actually required heating so that the lines would remain clear, which was sometimes it was your job to think of the keeping the thermal the characteristics of the thrusters capable so that the thrusters would still work. That required some tricks to keep the heating balanced, especially during Apollo 13 when those heaters weren't always available, right?
Right, and on the command module, which is what we're gonna talk about, there were 12 thrusters and there were 16 on the service module in groups of 4, 90 degrees around the cylinder, and there were also 16 on the lunar module, and they controlled those 2 modules in roll, pitch, and yaw, and plus or minus X, plus or minus Y, plus or minus Z.
Right.
The 12 on the command module were used for re-entry during the return mission as they came through the Earth's atmosphere, and they controlled roll, pitch, and yaw. They didn't have any capability to control change in X, Y.
Got it. So let's.
Oh,
so sorry. I was just going to ask you about Apollo 13 because you mentioned the particular attention with the command module thrusters. So when Apollo 13, when things went south on Apollo 13, I imagine you had to hurry in to the mission evaluation room. Is that right?
Well, the first thing I was concerned about, of course, was the safety of the crew, because my good friend Fred Hayes was on the mission. He had been added to the mission just a few days before, when his replacement was exposed to the measles, and they decided they better not send him. So I knew Fred, and we both lived in a little town suburb of Houston called Pasadena, and we still until he moved back to Mississippi recently, we'd see each other at the post office and the grocery store and all that type of thing. Anyway, so the command module RCS had 12 little thrusters at the base of the cone that constituted the geometric shape of the command module, and they weren't used until you got ready to enter the Earth's environment after the mission. So they were sitting there, and they had the opportunity to get really cold during the mission, because the environment of space is cold unless the sun is shining on you. So there were little heaters all along the system, and then particularly we didn't even open a valve to let the propellants out of the tank until we were ready to come into the Earth's environment. Mm-hmm. And so when all the propellants are in the tank, 200 pounds of stuff in there, and it cools real slowly or heats real slowly. So you don't have to worry about controlling the temperature on the tank. But once it gets into those little 3/8 inch diameter lines that go wrapping around the base of the conical command module, feeding all of the 12 engines, then they have the opportunity to cool very, very quickly. And we had heaters on all those lines, so that was what I was concerned about. So when I went in, I said, well, what's going on? You know, what do I need to help you with? And they gave me the status, and they said, we have had to power down the lunar module because the service module energy system, the fuel cells, was gone due to the explosion in the service module.
And powering that down means no heaters, right?
Yeah, so there was no fuel cell power to run all the heaters. The command module ran off of batteries, which were designed only to operate during the few minutes where they're coming through the Earth's atmosphere, and they didn't have power to run all those little heaters, you know, for the next 4 or 5 days, and also be able to satisfy the reentry.
Right.
And the lunar module had no way to connect to the command module. Although we later figured out how to do that, but we needed that just to make sure they got back to the point where they could re-enter the Earth's atmosphere. So they told me when I got there, said, Norm, we're having to shut off all the heaters on the command module reaction control system. And I said, oh my God, you can't do that. You know, we've got a line that's got a little bit of propellant sticking out of the top of the tank and going to the system shutoff valve. And I said that line will get real cold. It'll freeze with no heaters. And they said, well, you better get together with some guys and figure that out, because we've already turned it off and it's not coming back on.
We're not asking for permission. They're telling you.
You know, we're trying to make sure the crew can get back alive. So I had worked with the thermal analysis people, and so I got together with my colleagues there, and we had predictions for the flight. So we changed all those predictions, and it looked like it was probably going to freeze. So we used as much as possible a technique we call passive thermal control, PTC. And what that is basically you turn the side of the spacecraft toward the sun, and then you use your little thrusters just to rotate very, very slowly, about 1 revolution per hour. And we call that the barbecue mode. So it was just like you had a...
Because it's turning on the spit.
You had a pig on a spit, and it was turning real slowly so that everything, you got a little bit of heat once in a while, you know. So that we knew that.
You said, did you say once per hour, right?
Yeah, that was the typical one. I'm not sure whether they speeded that up or not. I really can't remember. But the typical PTC mode was turn, and you use your little rocket engines, like I showed you on the service module, just to start the spacecraft slowly spinning, and then it's kind of like really a barbecue.
And did you model that beforehand? Like, did you predict?
Oh, yes, we knew exactly how it should respond. We had done tests in a vacuum chamber to make sure we had modeled it.
Because you had a copy of the spacecraft on the ground.
Well, yeah, but we had also 2 years before or 3 years before, we had taken a whole spacecraft, put it in our big vacuum chamber with some simulated sunlight, looking at the side, and had it rotate on a rotating base that it was sitting on. And we had hundreds of thermocouples all over the place watching the temperature. So we knew
you had all the data. Yeah,
we had all the data, and we could predict that kind of thing. So we knew that would work.
Yeah, that's an interesting part of the story that I don't think a lot of people have heard about. That obviously for the small command module to get back, they needed to be able to have reaction control system, and then keeping it from freezing required that slow rotating. That's really neat. Now you and I were talking before. You were saying that every successful Apollo mission was a cause for celebration, but in particular 13 led to some pretty happy, was a happy time. Tell us about how it felt to see that spacecraft come down successfully.
Oh, everybody had been on pins and needles, and really very, very quickly after the problem occurred, and it was determined what the issue had been. We had Tiger teams forming in the Mission Control Center, figuring out consumables. Was there going to be enough oxygen to breathe? Was there going to be enough water to drink? Because the fuel cells, their waste product is water, which went into a tank, which the astronauts planned to drink during the mission. So they got thirsty on the way home because there wasn't that much water. Yeah. So anyway, there was a number of things that additionally could have gone wrong. Nobody had ever planned for the explosion of a supercritical oxygen tank, which was the way that the oxygen was fed to the fuel cells. So it was touch and go until we got on the way back, and we were able to determine that we had powered down the lunar module, and it looked like we were going to have enough power to get what we call Earth interface, where they would drop everything except the command module, and then the command module batteries, which had not been used, were sufficient to get them through the Earth's atmosphere. So when the pictures from the area of Samoa where they came down, we first saw those three big orange and white chutes coming out with that little command module hanging down underneath them, and then we got bigger and bigger and bigger as it descended, and we saw the splash.
Right.
And then the chutes, collapsed into the water. The Navy guys, the SEALs, were right there,
Right.
and they put the flotation collar underneath the spacecraft and got the hatch open. The guys climbed out into the rubber raft. That was, everybody, was hooping and hollering and carrying on. Everybody in my cadre and in the Mission Control Center smoked in those days.
Sure.
Cigarettes hadn't been realized as the danger that they are. So all of the cigars came out, and the Mission Control Room was full of cigar smoke because everybody clapped each other on the back and smoked their cigars and that type of thing. Well, those of us that weren't mission controllers or the mission director at that point could leave. So we headed out, and there was a stream of people heading out all of the buildings, heading for the parking lot to get in their cars to drive across the street where all the bars were located. And suddenly it dawned on everybody that if we all get in our cars and try to drive across the street, there'll be a huge traffic jam and there's no place to park over there. So people just walked. There's about a half a mile walk out to the gate from where we were, and then that's right across the street from the commercial area. Wow. So there was, several thousand people heading down the street, heading for the gate, going across. They just made the traffic stop, headed across to the bars, and the beer flowed. I tell you. So,
all right. Well, that's fantastic. I'm going to finish up with one last question for you. It's been 50 years. This is, as I said before, the mission of 13 was one of the things that people remember most about the Apollo program. But more generally, I mean, this experience that you lived through, and you helped get that crew back safely. But having gone through that, what are some lessons that you learned from that, and that maybe you take today? I mean, in terms of people working together to get things done, or anything like that. How did it impact your professional and personal life? After that.
Well, it was just a great example of the NASA ethos of how we worked. Our way of approaching things is the guy who leads the meeting is the one who knows what he's doing, or he or she. And so when we were talking about the RCS, the people that were very much senior to me, they shut up and they listened and they took my word and they trusted me. Right. And when somebody else needed to talk and do something about another area, they talked. So there was really no hierarchy in these meetings. It was just who knows what and who's got an idea about what we can do. And that was always with us and has stayed with us. And it saved other problems that are not as well known in the Apollo program. And in the shuttle program that came later, as you know, we lost two crews, That's right. Challenger and the Columbia, and I participated in the follow-up to both of those. I lost friends on both of those missions, and that's a hard impact. But the lesson is try to think of everything possible that could go wrong, and then analyze it and come up with a plan so you've got it in your hip pocket. At least the outlines of how you're going to approach the solution.
Great. All right. Well, thanks everybody for joining us here from the Adler Planetarium. But especially, I want to thank Norm Chaffe. This has been a great discussion. Thanks for joining us today, and good luck with everything.
Hey, can I say one thing to the young people who may watch this?
Actually, Norm, please do. Yes.
Okay. It was my great good fortune to be able to work for NASA, coming basically right out of college with a master's degree in chemical engineering, very brief time working for an oil company, and then came to NASA because I always loved the idea of going to space. So it was my great pleasure to know those early astronauts, to work on every spacecraft: Mercury, Gemini, Apollo, Space Shuttle, International Space Station, etc. Planning for Mars exploration, which is now going to happen in the next few years. And I'm so excited. I'm 83 years old, and I'm hoping to last until some folks get to Mars and walk on the surface of Mars. And you young people that are looking at me today, and even the 20 and 30-year-old young people, you will be alive when we do go to Mars and get to Mars, and your children will be the people who first walk on Mars. The Neil Armstrong of Mars is alive now and probably has visited the Adler Planetarium. I'm planning to last that long in order to see that. But I want you to know that this is coming, and other kinds of things, and look forward to it. I hope some of you young people will follow my example, go into the aerospace business, and lead us on to Mars and wherever we go from there.
Excellent. I can't think of a better way to finish. Thanks so much, Norm. It's been a great pleasure, and thank you all for joining us today. Take care.
My pleasure.
All right. Take care.